All right, good morning, class. So for today, we're going to be moving on into Chapter 2. And our first section is going to be Section 2.1a and b, which is our goal for today. So 2.1, we're going to be start to having our introduction to limits. Why do we care about limits? Well, again, when we get into Chapter 3 and we start talking about derivatives, then we're going to have the limit definition for a derivative. But in order to talk about that definition, we also need to know about limits. So this is where we start. But just as a beginning introduction to limits, if you're new to limits, that's all right. That's fine. I'm not expecting any prior knowledge per se, but we are going to cover the basics of limits today so that you should have a good footing for what's going on here. So we're going to start with looking at what are called left-hand limits and right-hand limits. Talk about what the difference is, what that looks like graphically, what are some examples where we can see that they're different or the same, what does that mean, so on and so forth. So that's the goal for today. All right, so we are looking today at section 2.1a. And again, let's just start with some vocabulary we're all going to need here. So first things first, we have what is called the left-hand limit. Now when we have this written out symbolically, this will be written as LIM for limit as x approaches some value a, and I'm going to put negative for the left for a function f of x. Now this, I put the negative here because if you think about a number line, negative numbers are to the left, positive numbers are on the right. So if you're approaching from the left, that's what a left-hand limit means, then you're approaching from the negative side, hence the negative symbol here. So left-hand limit, what does this mean? This means it's as x approaches a from the left, as x approaches a from the left, the resulting value is this limit. So the whole point is we have some function, right? And maybe it does something wonky, but we want to know, what's the value at a? Now, in the case of this graph, it looks like we could just plug it into our function and we'd be able to find out. But alternatively, we can also look at, okay, what is this graph doing as we approach a from the left? And as we get closer and closer to a from the left, this should equal the f of a value. So this is our left-hand limit. Similarly, we have what is called a right-hand limit. Right-hand limit. And we also symbolically write this as the limit of f of x as x approaches a from the right. So it means the same thing as what we have up here, except from the right instead of the left. Right. So that's pretty much all I wanted to say about left-hand and right-hand limits. We can look at some examples to really see, what is this? So for a good first example, let's take a look at the function f of x is equal to x minus 2 divided by x minus 1. Now, oh, that's not the example I wanted. Let me change that. That'll be an example later for something else. X squared minus 1. Okay, so as it stands, and let's say we're interested in the point when a equals 1. As it stands, if I try to plug in 1 to this equation, I'm going to get a 0 in the denominator, and that's going to be a problem. So I can't just plug it in and figure out what this is. So what we can do to remedy this problem, well, there's a couple things we can do. The first thing we're going to do is we can just try to figure out what it is using limits. So let's talk about what is the limit of f of x as x approaches 1 from the right. What is this value? So in order to do this, we can set up a little table, and you can use a calculator, or you can just plug in the numbers and figure it out for yourself. So remember, we're approaching from the right. So all we're going to do here is just plug in numbers to the right of 1 and slowly move closer to it. So I've got values of x I'm going to pick, and their corresponding f of x values. So I'm going to start with 2, because that's to the right of 1, and it's kind of close. But if I plug in 2, well, 2 squared minus 1 is 3. 2 minus 1 is 1, so I'm going to have I'm going to have 3 divided by 1, which is going to give me 3. Okay, so we know that if I plug in 2, I'm going to get 3. Well, that's not really close to 1 yet, but we're getting there. So let's go a little bit closer. We can say 1.5. And if we plug in 1.5, now I did this with a calculator, we get 4.5. Okay, well, we seem to be moving in an upwards direction, so we've got a higher f of x value. But 1.5 is still kind of far from 1, so let's go a little bit closer. Let's try 1.9. Well, now we get 4.9. Okay, well, it seems like we're kind of getting close to 5 now, but we're not really quite sure if that's what's happening. If we're going to go past 5, will we get closer to 1? Oh, I'm copying the wrong problem again. Excuse me for a moment. Those are the wrong values right there. Sorry. When we plug in 1.5, we're going to get 2.5. So when we plugged in a number that was closer to 1, 1.5 is closer to 1 than 2, then we resulted in a value of 2.5. But we still want to get closer to 1. So we're actually going to pick something like 1.3. That's a better number to pick. In this case, we get 2.3. So we're getting smaller, but we're decreasing less. We can then pick 1.1, which is going to give us 2.1. We can pick 1.01, so I'm getting really, really close to 1 now. And I get 2.01, or if I pick 1.001, and as long as I keep adding zeros, this number here is going to get closer and closer to 1. So I plug in this number, and I'm going to get 2.001. So what we can determine from this is, as we pick numbers from the right of 1, as it gets closer and closer to the value of 1, our f of x values are getting closer and closer to 2. So we say the limit of f of x as x approaches 1 from the right is 2. So there's an example of the limit from the right-hand side. If that didn't quite make sense, don't worry about it too much. We are going to be having the Q&A later today, so we can hopefully answer any questions that you guys may have. Alternatively, if you're not sure what this limit is supposed to look like, then you can also try graphing this. Now, luckily, we can see that the numerator is factorable. So the factor, or the numerator I mean, will factor into x plus 1 times x minus 1. So these are conjugates of each other. When you multiply binomials that are conjugates of each other, which just means that they have the same coefficients, the only difference is that they have an opposite sign in the middle. But when you multiply conjugates, then what you get is you'll have your squared of the first guy on the left, and on the right, you're just going to have the right number squared. The middle term is actually going to cancel when you multiply conjugates against each other. So this is a nifty trick. So whenever you see an x squared minus a perfect square, you can always factor that into its conjugates. But point being, excuse me. Point being, we can factor the numerator like that, and we still have x minus 1 in the denominator. Well, now I can cancel these, and really this function is equivalent to x plus 1. Now you have to be careful here. The reason I say equivalent and not actually the same is because the original function was actually written as a fraction. So we still have some issues when we try to plug in 1, but we at least know that this is equivalently represented by x plus 1. So be careful in that differentiation there between the two. So we have it written like this, and we can now graph that function. That's a slope of 1 with a y-intercept at 1. So it looks something like that. And we're curious about when x is 1, when a is 1. This is 1 here. Well, slope of 1, that's going to be a value of 1, 2. Well, 2 for the y value, 1 for the x. And so we can see that graphically this lines up with what our limit from the right-hand side says it should be. So this is good. And that's our first example of a right-hand limit. So let's keep going. And we're next going to look at taking the limit from the left-hand side. So we are looking at, for our next example, say we have a function. Oops. Oh, this marker's dead. That's too bad. I guess we're stuck on black and purple. Alright, that's fine. So let's suppose we have a function, g of x. And this function is going to equal x squared plus x minus 6 divided by x minus 2. Now again, just like our previous example, we kind of have this issue of, well, if I plug in 2, I'm going to have a 0 in the denominator, and that's bad. We don't want to do that. So in order to try to figure out what this value is when x equals 2, we can use limits. So this time, we're going to ask ourselves, what is the limit as x approaches 2 from the left for this g of x function? This is what we're after. So we can use the same kind of trick we used before. We have x, we have corresponding g of x values, and I'm just going to plug in numbers that are to the left. So we can start with 1. That's to the left of 2. So when I plug in 1, and I'm just going to go ahead and write these down pretty quick, we're going to get a value of 4. But we can get closer to 2. So let's try 1.5. We plug in 1.5 and we get 4.5. Then I plug in 1.9, 1.99, and 1.999. The whole point here is I'm supposed to get closer and closer and closer to 2, because that's the number I'm trying to approximate from the left side, from numbers that are less than 2. So when I plug in 1.9, I get 4.9, 4.99, and 4.999. So what does this tell us? Really, this tells us is we're getting closer and closer to 2. our value here is getting closer and closer to 5. So that is the right-hand limit. Now, again, aside from using that approach, you also have the option of trying to graph this. Well, in order to graph this, we'd like to be able to factor the numerator. So, okay, let's try factoring that. So we're going to have an x times something with an x. We can see that we've got a negative sign up here on the -6. So we're going to have opposite signs. And then this number on the right side is going to have to be factors of 6. So I could do 1 and 6, but that's not going to subtract to give me 1 in the middle. I could do 2 and 3. In fact, if I do 3 minus 2, that's going to give me a positive 1 in the middle, and so we're good. We have this factored now. And lucky for us, it will then divide out with our denominator. And so this is equivalent to the line x plus 3. We can go ahead and graph that real quick. 1, 2, 3. Y-intercept of 3. It's got a slope of 1. So if I move 1 over to 1, then it should move up 1. So that's going to be at 4. At 2, that's going to be 5. And so I've got this line for this function. And when I plug in 2, according to the graph, it looks like it should be 5. So again, the limit from the left-hand side agreed with the graph representation. So this is good. We can see that, okay, this all lines up, the numbers make sense, and we have our left-hand limit now. So these are examples where the left-hand and right-hand limits are relatively easy to find. They line up with the graph, so we don't have any contradictions. It looks good, so nothing too confusing just yet. So let's go ahead and move on to another example where the left hand and right hand limits may not agree. In other words, you might get different values for the left hand limit and the right hand limit. Okay, and I forgot to lock the feed in place again. Keeps moving around. All right. Let me make sure this stays in focus. Yeah, okay, good enough. So, right, next example. So, we would next like, sorry, can't talk. We'd like to next look at a piecewise function. Now we've looked at several of these examples, but especially in this case, we can run into a lot of examples where the left and right hand limits are not going to agree with one another. So, I would like to have this piecewise function be 1/2 x if my x value is between 0 and 4. So if I have an x between there, and then I'd like it to be x minus 1 if x is greater than 4. So I've got these two different lines that will be graphed depending on which values of x I plug in. So what does this look like graphically? Well, let's just start with something easy. It looks like this only accounts for positive x. If x is between 0 and 4, we do this. If x is greater than 4, we do this. This doesn't say anything about if x is negative. In that case, because it doesn't specify anything for a negative x, we don't have anything to graph with it. So we actually don't have negative values of x. Negative values of x are not a part of the domain for this function. So we can just graph based off of the x's we're given. So from 0 to 4, we have this 1/2 x graph. So we plug in 0, and we're going to get a value of 0. So here's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this has got a slope of 1/2. So that's a rise of 1, run 2. So rise 1, run 2. That gives me a point here. That's at x equals 2. Rise 1 and run 2. That's at the x value of 4. 1, 2, 3, 4. And we're good. Because this 1/2 x line is only used for x values between 0 and 4. So there we have it. Now we have the x minus 1 graph if x is greater than 4. So we can go ahead and figure out, what would it be if I did plug in 4 here? 4 minus 1 is 3. So that would give me a value at 3, which is 1 above this value here, which is 4, 2. This top one instead is 4, 3. And I write this as an open bubble circle. That's because I can't actually plug in a value of 4 here. So that's not what the graph equals when I plug in 4. But if I could plug in 4, that's where the point would be. So I have it labeled there. And so we can move on for x values greater than 4. It has a slope of 1. So that's rise 1, run 1. So I'll have a point here, a point here, a point here, so on. This will keep going for positive x. Now, you may already be able to pick out the problem here. If I look at, what is the limit as x is approaching 2 from the left of h of x here? Well, from the left, if I approach from the left, so numbers less than 4, oops, sorry, not 2, we're looking at 4 here. For values of 4. So we're approaching 4 from the left. So we're here, we're here, we're here. We're getting closer and closer to 4, and we're getting really close to this value of 2. But if we look at the limit as x approaches 4 from the right of h of x, well, then we approach it with values of x that are greater than 4. So we're getting closer and closer and closer and closer. And we're getting really close to this circle dot that I have here. Well, that's getting really, really close to this value of 3. So as we approach this point from the left and right, we actually get two different values because this piecewise function at this point starts from two different places. So this is an important thing to keep in mind, especially as you're working through your Hawks Learning examples, your Hawks Learning Certify questions. You're going to be seeing many questions where they'll just give you a graph and they'll say, what is the limit from the left side at A? What is the limit from the right side at A? So it's very important to get used to this idea of approaching from the left and approaching from the right and realizing that it could very well potentially give you different values. So keep that in mind as you work through those examples and homework problems. So we would next like to discuss one more example for 2.1a. So this is not going to be a piecewise. It's going to be another fraction, except this is going to be a fraction that we can't simplify. In other words, we can't factor the numerator in order to divide out the denominator, and so we won't be able to graph it and make it look nice in any way. So it's a little bit messier to work with, but it's a good example to be aware of as you encounter some of these examples. So let's suppose f of x is equal to x minus 2 divided by x minus 1. Now in this case, I can't factor this numerator in order to divide out with the denominator. There's no way to factor this. This is the simplest form right here. So if I plug in x equals 1, or if I have a equals 1, well, that's going to be a problem. I'm going to have a 0 in my denominator. So what we can do instead when we think about this is we've got to think about what are our possible horizontal and vertical asymptotes. This is about thinking about what is our possible domain and range here in order that we can possibly graph this. So we already know that vertical asymptotes for vertical asymptotes, this is all about looking at the denominator to find your possible guys. Now in case of our last problem, if you could divide out the denominator, then you don't have to worry about it. But in this case, we can't divide it out, so we need to think about it. So where do we have problems? Well, the problem is when x minus 1 results in 0, or in other words, when x equals 1. So there's our vertical asymptote then. But let's keep going. So we got our vertical asymptotes. Horizontal, because you can have them going in both directions. Horizontal asymptotes. This has to do with looking at the numerator and denominator. So there's a few rules you can use in order to determine what is the horizontal asymptote, if there is one at all. So the first thing you can check, if the power of your denominator is greater than the power of the numerator. Now when I say power, I'm referring to what is the highest order for each denominator and numerator. What is the highest power that is included here for x? Well, in both cases we have x to the first power. So they actually have equal power, and so this first rule won't apply, but this is still a good rule to keep in mind. So if the power of the denominator is greater than the power of the numerator, then you have a horizontal asymptote at x equals 0. In other words, the x-axis. And that's because if the denominator has a greater power, then the denominator is going to be increasing much faster than the numerator. And if you're dividing by a bigger and bigger number, then if you think about it over time as you divide by a bigger and bigger number that is getting bigger and bigger than the numerator, then you're going to tend towards 0. And so that's why we have a horizontal asymptote there at x equals 0, the x-axis. Now, if we flip it and the power of the denominator is less than the power of the numerator, then there's no horizontal asymptote. And this is kind of true by a similar reasoning that if the power of the numerator is bigger than the power of the denominator, the numerator is getting bigger and bigger and bigger very quickly. And it's getting to a point where it's growing so much faster than the denominator that regardless of dividing by some number, it ends up not really mattering, and the numerator is going to overpower the denominator. Well, when the numerator overpowers, then really we're just dealing with whatever's in the top. And so we don't have any asymptotes in that case. It goes wherever it wants to. So that's the second case. Now again, that doesn't apply here because our powers are equal. So for our third and final case, if the powers are equal, then you have your horizontal asymptote at x equals the fraction created by the leading coefficients on x. And this is referring to x with the greatest power. So what does that mean in our case? Well, our leading coefficients are 1. So 1 divided by 1 is 1. So here we actually have, based on these rules, a horizontal asymptote at x equals 1. So what does that really mean graphically when we try to graph this? So we've got x, got f of x. We have a vertical asymptote at x equals 1. And that's just because if we try to plug in 1, then we get problems. We can't do that. So we got a vertical asymptote right here. Now we also have a horizontal asymptote at 1. So here's the horizontal guy that we can't cross. Okay, so we have our asymptotes drawn. Now what? Well, now we just start plugging in some values and try to figure out what's going on here. So this is at 1, 2, 3, 4, 5, 6. This is 0, -1, -2, -3, -4. So if I try to plug in 2, well, I'm going to get 2 minus 2 is 0. 0 divided by a -1, so that's just 0. Okay, no big deal. So that gives me a point. If I plug in 3, then I'm going to have 3 minus 2 is 1. 1 divided by 3 minus 1 is 2, so that's a half. So I have this value that's halfway up to 1. Well, in reality, and you can see this if we were to go with our other approach, if we look at the limit as x goes to positive infinity, and we're looking at this from the left, if we're approaching positive infinity, which is way down here on the x-axis, forever that way, as we get closer and closer from the left side, what is happening to our f of x? Well, as it turns out, if you plug in, let's see, this 1, 2, 3, if you plug in 4, then you plug in 5, you plug in 6, so on and so forth, you're actually going to get closer and closer to 1. So that's what's happening with our graph here on the right side. Now, we still have this space to fill in, what's going on right here between 1 and 2. Well, for that, we want to think about our limit as x approaches, this is when x is 1, from the right. And again, we can try to plug in values that are to the right of 1. So I already know if I plug in 2, then I'm going to get 0. But if I plug in, let's say, 1.5, well, 1.5 minus 2, that's a negative 0.5. Yeah, 1.5 minus 2, that's going to give us a negative 0.5. So if I plug in 1.5, 1.5 minus 2, that's going to give me a negative 0.5 divided by 1.5 minus 1, 0.5, that's negative 1. So I'm down here. if I plug in 1.25, then I'm going to have a negative 0.75 in my numerator. And then in the denominator, I'm going to have 0.25. Well, 0.75 divided by 0.25 is 3. So we've got a negative 3. And what you can see is just by shifting the x value by 0.25, my y dropped quite a bit. And so what we've got here is as we get closer and closer to 1, so we got negative 1, negative 3, this negative number is dropping very quickly. And that's because this negative number in the denominator, as we get closer and closer to 1, from the right side is getting smaller and smaller and smaller. 1.5, 1.25, 1.1, 1.01. This denominator is getting really, really small. And when you divide by a really, really small number, your overall number is going to skyrocket. Now you can play around with that on your calculator to test that idea. But what you're going to see is as you divide by smaller and smaller numbers, your resulting answer is always going to skyrocket, whether it's positive infinity or negative infinity. So the limit, as we approach 1 from the right side for f of x, this is actually going to negative infinity. So the whole point of this example is to really get used to this idea of, what is infinity? Can we approach infinity? What happens when our function starts it just drops off and disappears somewhere? You can have answers where your limit goes to infinity, and you can also take limits that are approaching infinity. It's asking what is the function doing in the long run. Especially in the case where you have a horizontal asymptote, this line can never cross it. So it's forced to either approach 1 in the long run, or it would have to bend down and disappear. Well, we already tested some values to see that it is approaching 1, so that's what's happening here as x goes to infinity. Now, for the sake of time, if you do the same thing over here on the left side, then let's see, if we plug in 0, then we can have negative 2 divided by a negative 1. That's a positive 2. So we got a value up here that's above our x equals 1 line. Or, I'm sorry, that's y equals 1 for the horizontal asymptote. Y equals 1 here. Yeah. When you plug in values here, then it's actually going to go up this way and down that way towards the asymptote. So what does this tell us? Well, this tells us that the limit as x approaches 1 from the left of f of x is really skyrocketing upwards towards positive infinity. So these are perfectly valid answers, but we can also see is that the left is going up and from the right it's going down. So we have these conflicting results. So in 2.1b, we're going to dive into more in terms of, what does it mean when this happens? So let's go ahead and change gears real quick. All right, so we're going to change gears to 2.1b. Now the first thing we'd like to discuss is, okay, we've talked about limits from the left side, we've talked about limits from the right side, but what is the actual limit of a function if we're not talking about left or right? Well, we have a definition for that. For a function f, and real number t, if the limit as x approaches t from the left of f of x is equal to some value L, and the limit as x approaches t from the right of f of x is also equal to L, so they're equal to the same value from the left and right, where L is a real number then the limit as x approaches t of f of x is equal to L. Now notice symbolically this limit doesn't have a plus or minus here. This is the true limit of the function as x is approaching t. In order for the limit of a function to equal anything, the left and right hand limits have to agree. They have to meet at the same point, and when they do, then the limit of the function is equal to that. So in this case, we say the limit exists. In other words, this limit for f of x as x is going to t, it exists. It's some value because the left and right hand side agree. Now, this statement is also true in the reverse. If the limit exists and the limit equals something, then that tells you that the left hand and the right hand side equal each other. So this is an if and only if statement. It's true both directions. If the limits from the left and right hand side are equal to each other, then the limit is equal to L. But vice versa, if the limit exists and the limit is equal to L, then the left and right hand side limits have to equal each other. So this is an important statement, and it's one we're going to need to keep in mind when we start talking about, does the limit exist or does it not exist? So the next case, oops, no number. So the next case we would like to discuss so if we talked about what happens if they equal each other, but if the limit as x approaches t from the left of f of x does not equal the limit as x approaches t from the right of f of x, then the limit as x approaches t of f of x does not exist. Or in other words, you can abbreviate that as DNE. Does not exist. Yeah. So in the case of our last example where we had this graph with the two asymptotes here, we had one on the left side going like this, and we had the other on the right side going like that. When we looked at this value of x equals 1, we had that from the left it was going to positive infinity, and from the right it was going to negative infinity. In this case, the limit at x equals 1 does not exist. So this is a good example of where this can happen. We also saw an example with our piecewise functions that we had a graph that looked like this, but then maybe it picks up there and then goes somewhere else. In this case, from the left side, it equals this point, but from the right side, it equaled the open circle. That's another example where the limit does not exist. So you need to be careful and differentiate between what does it mean to take the left-hand limit, the right-hand limit, but what is the actual limit? The actual limit requires that the left and right-hand side agree. If they don't agree, then the limit does not exist. But keep in mind that if the limit does not exist, you might still be able to find the left and right-hand sides. They just may not agree. So let's see, we're running out of time. There was one more vocabulary term I wanted to pick up with some other examples, but I don't think we're going to have time to get through all of that. So I may actually just save that for the next video, and we'll talk about it then. So this is your crash course introduction to limits. Of course, we will have a Q&A later today. If this is not adding up, by all means, send me questions, send me emails. Let's talk about it. Otherwise, I hope things are working out and wish you the best of luck. All right, that'll end our lecture for today.